All right, I think we got most of the stragglers in and seated, so why don't we go ahead and have some fun. So just to make sure everyone's in the right room, including myself, this is going to be a kind of a walkthrough around a lot of the choices and process involved in building out large-scale services on Azure. So my team, the Windows Azure Customer Advisory team, but we may not be called that anymore, but anyway, Azure Customer Advisory team. We work with customers, internal and external, on about 500 to 600 projects every year to take some of the bigger, nastier, more interesting things, get them up and running, find things when they break, all that kind of fun stuff, with the goal of taking it back to engineering, making the platform better, as well as publishing guidance on how not to have exciting learning moments in production. So, who's had an exciting learning moment in production? Everybody else has bad monitoring and didn't know it happened. Okay, so this is meant to be as interactive as is possible with such a large audience. I will ask you to use the microphone, mostly because I cannot see you. If you're not using the microphone, I can't hear you, and with the lights, I really can't see much of anything. So please use the mics. Please ask questions. Please be interactive. If I throw out something that seems a little interesting, I may be doing it just to see who's paying attention, so please call me on it, ask questions. This conversation will largely go where you guys want it to go. We're going to talk through a lot of customer stories. We're going to talk about a lot of architecture. We're going to talk about a lot of patterns. Ultimately, what I want to do is show you guys how we go through taking one of the projects that we're asked to look at, breaking it apart, looking at, does it scale? Will the lights stay on? Can we afford to build this thing? And more importantly, can we afford to build the second version because we didn't incur so much technical debt in the first one? It won't be so much a discussion on, hey, how do I build a service for 100 million users? I can tell you guys, it's fairly straightforward. It's simple. It's hard, but it's simple. What I'd rather do is kind of walk through the process and illustrate to you whether you're building something for a fairly fixed user base, whether you're getting ready to go viral or you're hoping to be wildly successful. We all hope that. The same process, the same questions, the same way of going through and teasing apart a design and seeing if it will scale, seeing if it will stay up, is largely the same. So, okay. This will not be a discussion of features. I will only discuss an Azure feature or a tool or a technique in the context of a pattern. Tomorrow at 1 o'clock, I'll be doing another presentation that is the pure code version of this one, which is colloquially known as, here's all the anti-patterns that I'm ashamed that I've seen in code and written a few myself that I want to show you guys in hopes you won't have to find the same. So we're going to focus on architecture. We're also going to focus on choices. And the theme I'll keep coming back to is that there's no really kind of magically right choices when it comes to cloud architecture. There's always a trade-off. What am I going to give up for what am I going to get? If I make a choice, is it more expensive and more complicated to build, but do I get better scale or availability? Always these trade-offs. So if I had one magical perfect architecture that worked for everything, well, I'd probably just be patent it and make a lot of money. But since one doesn't exist, we're just going to talk about choices instead. And we'll walk through that. I've got a synthesized real-world scenario that I've put together, and we'll just walk through and tease it apart. So if this doesn't sound interesting, there are several other really great sessions that you should totally go check out, because otherwise you're going to find this really boring. In case this does sound interesting and applicable, lean back, enjoy the ride, and let's have some fun. Cool? A few nods. Actually, I have no idea if you're nodding or not. So I'm going to start off with just a little bit of philosophy before we dive right into the guts of the architecture, because much like cloud and big data and many of these other buzzwords, they generally mean whatever you need them to mean in the context of whatever you're trying to sell, right? Well, so let's come up with just kind of a terminology for 4 pillars of any cloud service that we can use to wrap a discussion around. Specifically, scalability, availability, manageability, and feasibility. And they're all tied together. You tug on one, the rest will move. So when I think about scale's a really interesting one. It's really only 2 things. Can I throw enough resources and capacity at a problem, which is simple but hard? How do I go from 1 unit to n units? Surprisingly, fairly challenging. And once I've deployed enough capacity, how efficiently can I leverage that capacity to solve a problem? The joke I usually tell is, if I need to do 1 million operations a second, and I can put a single operation per second on a VM, and I can throw 1 million VMs at the problem, I don't have a scalability problem, but my bottom line probably hates me, and my CFO is going to be coming after me with a big stick. So it's this interesting balance of, can I throw enough capacity, and then can I marshal it efficiently? Do I have good code paths? Am I using my deployed capacity effectively? More traditional performance tuning. And the interesting thing about moving from capitalized investment of hardware for a target 2 to 3 years from now, our usual CapEx buying cycle, to a multi-tenant shared compute fabric that is elastic, it exposes a lot of the interesting code patterns that we've been using for a long time. And I'll talk about some of those. And scalability and availability are really tied together. If I can only scale to 10,000 ops a second and I need to sustain 100,000, oh great, for all intents and purposes, I'm actually down. I'm not available. If I'm always, but if I can do 1 million ops a second for 3 minutes a day, depending on the workload, that might not be all that interesting. So availability, I tend to phrase as, can my application endure transient or sustain transient enduring faults? Networks will hiccup, disks will fail, stuff will blow up. If you're going to deploy enough machines, you cannot build titanium eggshells. I cannot build a bespoke scale-up server that is 35 ways redundant. Well, I could build one of them, but building 2 is challenging. And they get very expensive. This is what we do traditionally in bespoke data centers. We've gotten very good at it in the last 30 years. The challenge is, when I buy that wonderful iron beast, I'm buying it not for today, not for tomorrow. I have to buy it for 3 years from now. And if I'm working in a world where my load is unknown, it's dynamic. If I do sporting events, if I have to buy for my peak, I'm wasting a lot of money. If I'm working on a kind of an open web-facing experience and I am popular, I'm successful, I don't know what to buy for. So these are some of the things that really kind of make moving into cloud, especially public cloud, where those investments are amortized across a bunch of folks, really attractive. But it comes with a bunch of different set of trades. We're basically trading physics for economics. That's really what cloud comes down to, at a certain sense. And those physics come with a few interesting assertions. They break a lot of ways we've built software. So I'll kind of dive into some of those. The third one is probably the one, I'm not going to talk about it a lot today, but it's one that I spend most of my time on, which is when I move from managing a collection of VMs, and a relatively small collection of VMs, to managing a collection of services at scale, many of which I don't even own or control. This becomes a very nuanced, very interesting problem. And we could, if I had, you can usually, when I'm talking to a team or talking to a customer, I can tell if this is their first or second cloud service, if the first or second question is, how am I going to monitor this thing and patch it in production? So it's probably the most important one, because if you can't monitor effectively, you don't know if you have a scalability or an availability problem. And I'm going to borrow a quote from someone. I can't remember the name, but I'll look it up later. Nobody calls you at 3 o'clock in the morning to tell you what a great job you did. So I totally stole that one. But the last one's actually really interesting too, which is feasibility. Can I afford to build the thing with the engineering talent that I have and can retain and can bring on in a time frame that makes sense for the business I'm trying to run? Simplicity is generally always going to win. Not to say that we won't have sophisticated systems and sophisticated architectures, but complexity for the sake of complexity does not work in a large-scale application in the cloud. You can't move fast, you can't find issues, you're running around with lead weights attached to your legs. Great for training, not so great for a cloud service. So a lot of the times we'll look at taking more traditional enterprise 3-tier apps and a lot of those patterns and classic SOA and going, what can we remove? What can we pull out in order to have fewer moving parts in our system? It's easier to build, it's easier to manage, and it's easier to run. So, seem like 4 interesting things to wrap a discussion around? And no one's yelling no or running out, so I'll take that as a yes. Okay, just diving into scalability a little bit more. Scalability, capacity times density. This is the equation that will govern how much effective work I can put through a system. What are the metered resources? What are the contention points? What are the choke points? We probably all spent a whole lot of time in school or learning on the job about multi-threading and concurrency and contention in threads. Okay, that happens on one box. In one box, well, let's be honest, nothing interesting happens in the cloud on a single machine. Interesting things happen on lots of machines. So now I have contention inside a VM, I have contention across processes, and I have contention across services, and sometimes in the most interesting of ways. How do I add additional capacity? Adding capacity when someone else is marshaling affinity is easy. So, an example, if I add another VM behind a load balancer, that was relatively straightforward. I add more capacity, the load balancer recognizes it, and provides affinity for incoming work. Going from one database to 2 databases is really hard if you're essentially having to do horizontal sharding. So there's a gamut of, some things are easy to add more capacity, even after the fact. Some things are very hard, and you have to plan for them up front. There's also a bunch of subtle, interesting things that happen both in our programming languages and our platforms, as well as in the underlying infrastructure. And if it's not, completely banned, I'll tell a few Amazon stories here too. So, but then it flips over to using capacity more efficiently. And the traditional performance tuning, folks using async await, for .NET folks in the room. Okay, so the design target that I look for when I'm thinking about operations per second per core, which is ultimately the economics I'm looking for, with a fully asynchronous web API is about 5,000 operations per second you should be able to sustain, with somewhere between 20 and 22,000 active connections per core for a full SSL negotiation. So the difference in terms of economics between a fully synchronous blocking web front end that can do 12 connections per core by default concurrently, and being able to do 20,000, this starts to add up very, very quickly. We've actually hit this a bunch in some of our internal services when we're trying to bring COGS down, because we've already solved we can throw as much money at this to solve the problem as we need to. Relatively straightforward improvements in that front-end web API experience add up to millions of dollars a month very, very quickly. So we'll dive into some of those as well. Also, collapsing tiers. 3-tier app, web, app, data, the one true way of doing things, right? Obviously, it's a leading question. In a world where I do not have an explicit security boundary between my web tier and my app tier, doing a full network translation with protocol serialization across the wire is taking a pile of money, putting it on the ground, and lighting it on fire. This is a historical relic for cloud services, unless I explicitly bake in that security boundary, which I may want to do for some things. What I see as kind of the new 3-tier app is front-end processing, back-end processing through a queue, and a collection of data tiers. And ultimately, network performance, because these are all, well, distributed systems are distributed, and that's both a blessing and a curse. So enough philosophy. Let's dive on in and look at an app. So this is a mix of 2 or 3 real ones. You can guess what it might be, but you probably get it wrong. So assuming I'm a fast food vendor, I've got thousands of stores out there, and I'd actually like to have some real-time BI, some real-time insight into what's going on in each of my stores. My customer wait times, my orders, my deliveries, all that really interesting ambient business data that just kind of tends to fall on the floor right now. We can think of any number of business business operations that could be tuned, as well as the value of the data itself in terms of purchasing behavior. Sounds a little creepy, but that's the way the world works these days. And assuming that I wanted to be able to publish some updates to a central service. What did I say, server? That was a Freudian slip. To a central service every minute or so. And let's just say it works out to about 5 KB of XML. I personally detest XML with every fiber of my being. It is another instance of taking a bunch of money and lighting it on fire. But a lot of times you've got stuff out there. Legacy systems, stuff that is in production, it's working well. It has weight, it has momentum. There's often either no ROI to change it, no reason to change it, or here be dragons, we have no idea what this does, just take the file and process it. Or somewhere in the middle. So let's start with a classic 3-tier architecture. This is the starting point. I've seen way too many of these lately. I come in, I hit a web roll, I grab some data, I do my validation, I do my authentication, I shovel it out to something that's actually going to execute business logic, and I drop down into a database. So far, so good. So let's tease this one apart and actually look at how does this scale, where are its resiliency and failure points, and are there things we could do about those in order to improve this? Apparently this is a directed clicky thing. All right, so let's look at our scalability points. I always like to draw basically the path of data through the system in a physical as well as a logical sense and trace it at each step. Every time I leave a process boundary or a system boundary, interesting things can happen. So if I deploy an Azure service in a single cloud service, whether IaaS or PaaS, I'm essentially running with a single VIP, a single virtual IP, and there's a software load balancer associated with that. Like anything else, there's a finite limit. It's pretty big. It's depending on how kind of intense you're going. And I can't give you an exact number because we reserve the right to make it better. Figure 60 to 120,000 sockets. So pretty substantial. And each socket gets about 5 minutes of idle time before the platform goes, that's actually a metered resource. That's valuable. You're not using it. I want it back so someone else can have it, even if it's someone else within your own service. So in this particular workload, I may have a few thousand stores. I don't think I'm really going to hit a scale limit here. If I was doing a smart grid system with direct connectivity where I had tens of millions of devices, this would be a problem, and I would have to add more capacity by deploying multiple VIPs. So in terms of VMs per cloud service, each VM gives me more compute, more storage, more network. If I need more, add more VMs. For a system of this scale, I'm really not worried about overrunning a, that's actually supposed to be green, not yellowish, because that means it's good. So we'll just all pretend it's green. Not really worried about a scalability point in terms of VMs or something of this scale. If I was looking at batch compute where I needed to deploy 15,000 cores in a burst mode, that might be a little bit more interesting in terms of having to basically partition up the cores and allot them across multiple cloud services. Whereas this one, it starts to break down, is the number of requests per second per VM. I know I can get that all the way up past 5,000 per core on a .NET, on a modern .NET 4.5 async stack, but I may not have built it that way. So that's something you need to look at deeply in terms of the implementation. Where this pattern would almost always break down, for very good reasons, is the backing stateful store. If I have one resource unit at the back, exemplified by one Azure SQL database, if I slip up and call it SQL Azure, do not tell on me. And it could be an IaaS VM, it doesn't really matter. I have one unit of state. And the way that we have an entire generation of developers, myself included, that learned through hard experience that we're going to build things stateless. We're going to make all that distributed systems goop the job of the relational thing at the back, and life will be great. And for a long time it was. But when I start adding in high insert volumes, dynamic load, shared hardware, and the need to be elastic, this starts to break down a little bit. And for Azure SQL Database, I will slip up, I know. I've got to think about some of the resources I'm getting metered on. The most obvious one is connections per database. A network socket's a valuable resource. In this case, I get capped at 120. 180. Any more than 180 on the default, basically cheap SKU, I get told to go away. Unless you change it, the default ADO.NET, I said ASP.NET. I looked at this slide like 5 times. How did I miss that? Anyway, the ADO.NET connection pool size is 100. So with 2 instances that are not managing, if they leak connections, I will blow that, I will basically lock myself out of my database. And there's a bunch of issues around, a bunch of things around database throughput, especially for a bulk insert, or essentially what could be a bulk insert workload. But it doesn't seem too bad. There's some ways we could work around that. There we go. You are, in this particular instance, since I didn't put any additional security between those 2 tiers, I'm just wasting money. Just lighting on fire for fun. Okay. So let's talk about SLAs. We'll talk about platform SLAs, and then we'll talk about real SLAs in terms of your ability to actually deliver value from a service. Is everyone familiar with this page? If not, go have a look. I apologize for the legalese, but the lawyers make us do that. So there's the nice human-readable SLA, and there's the detailed ones. You probably just want to read the human-readable ones. But then the key thing to take away is, what is the SLA target? What is the time frame that it's measured over? And what is the actual operational metric being measured? We'll dive into that in a little bit. So quick refresh on the 9s. Anyone working on 5 nines systems right now, where you basically get to hiccup and then you're out of SLA? Actually, I can't see any hands anyway. The really interesting thing about this chart is once you get basically between 3 and 4 nines, it becomes less of a platform challenge and it becomes a huge operational excellence challenge. You can have the best hardware, the best platform, the best software on the planet, but all it takes is one fat-fingered configuration update and you just blew away your downtime for 2 years. So it gets exponentially more challenging the further down this chart you go. All right, so let's talk about SLAs here. I've got 3 moving parts, therefore I've got 3 things to worry about. So in my particular case, I chose to use the Windows Azure Traffic Manager in case I wanted to do some geo-balancing. What I'm really doing there is setting up this, kind of leaving the door open in case I wanted to do multiple data center failover in the future. Kind of just left that in there as a teaser. The Windows Azure Traffic Manager SLA is 99.99% calculated over a monthly cycle. And the impact if it's down is that if I've already logged into the service and I have a cached DNS record or an active connection, I'm fine. I've already leveraged that service. I've cached the token, typically in the form of my DNS lookup. and I will continue to be fine. If I'm a new store coming online, or if I've dropped my connection and I need to go back and get another DNS token, I'll be down for that time period. But that's a pretty safe bet. That's a pretty rock solid service. For my cloud service VMs, I've got 3.5 nines of external connectivity. But implicit in the basically the failure mode for a cloud service or an availability set is that I have 2 fault domains, essentially representing independent physical resources, effectively the logical equivalent of a rack. And I can lose a fault domain. Doesn't happen often, but it can. Over enough time and enough pressure, it will happen, meaning I'll lose 50% of my capacity for a short period of time. So that becomes a scalability challenge. If I'm running at 80% capacity, if I'm running hot, and all of a sudden I'm now running at 140% capacity, unless I have something in the system that can shed load or handle back pressure appropriately, I'm probably going to blow up. So this is just an instance of availability and scalability being very tightly tied together. But here's the fun one. I got to bag on this a little bit. The SLA for SQL database doesn't say that you can actually execute work. It says you can establish a connection to the endpoint. You can still be unable to insert or select data because of a contended resource. So this is an area where, okay, if you look at the high-level SLA, it's okay, but we need to dig deeper and actually look at it in the context of the primary workload, which is, I've got some stuff, I need to put it in. So, and of course, SLAs are compositional. The more moving parts you have, the worse this number gets, which is one of the other reasons to keep looking at how do we go for a complete simplicity? How do we have fewer moving parts without giving up, without having to basically go back to file new transistor and build everything from the ground up? When we think about which pieces of the system do I want to choose a high abstraction service, like websites or SendGrid or one of these things, versus which pieces do I want to go fairly low in the stack, this control versus SLA and versus engineering investment is one of those key decisions you get to make. Isn't this stuff fun? Okay. So yeah, the calculation does not tell the full story. This is not the experience your application will have. This just helps bound the box for availability and help understand what they're doing in the kitchen. Okay. The different SLAs will be calculated over different time metrics. Some will look at 5-minute increments. Some will look at kind of aggregates over a week or a month. It's helpful just to understand them, just to get a sense of kind of what we're extremely confident that a service can deliver. As well as the success metrics. Can I connect? Will VMs be active? Will they have network connectivity? These are usually in the first couple paragraphs of the SLA definitions, and they're fairly easy to tease out. The most important takeaway, this is the composite platform SLA. This is not what you can deliver to users. We can give you the best VMs in the world, but if you basically throw an exception on every call, you're not delivering a lot of value. Unless you have an exception delivery service, which would be kind of weird, but I don't judge. Okay, so let's break this architecture down. Pros. Well, we all know how to build one of these, so it scores well on feasibility. Yeah, that's about all I've got to say about it. Sorry. Cons. This is extremely vulnerable to load spikes and back pressure. So if I'm sitting down and I'm designing the firmware or the application that's at the store, I probably have a little bit of OCD, kind of as an industry, we're a little prone to that. It's not bad. And I'm going to say I would like to send at the top of every 5-minute increment. I would like to send at a nice predictable rhythm, which works great for one store. And then I have 1,000 stores going, let's all send at exactly the same time, which, well, even with a few thousand isn't too bad. When you have 30 million, this is a real problem. Because essentially, you have these huge peaks and troughs in terms of the load profile for the system. And you need some way of handling that. And it's very similar to if we were all to stand up right now and rush at that door, then we'd jam up. And we'd jam up for longer than it would actually take for us to back off properly and kind of go out through. We'd all end up in these interesting waves trying to rush back through. Whereas at the end, when we all get up and leave in a calm, orderly, happy at having had awesome content fashion, it might take a while, but we're not going to get jammed up in the door. So it's part of that, how do we have rate leveling? How do we decouple parts of the system? Because in that implementation, there is a direct thread chain from the publishing, from the store, over the network, to the web, basically to the HTTP socket, over the ODBC connection or ODB connection or whatever we choose to use under the hood, into SQL, down to the underlying disk. There's nothing there to break that string. And if I get pressure on one side, it's going to flow all the way back through. I also can't prioritize work. Is it more important to receive new content than it is to deliver updates and BI? I can probably take a little bit of latency on the BI as long as I'm always receiving data from the stores, or vice versa. That's a business choice that'll be reflected in an engineering decision. Shared resources between workloads. This is probably one of the biggest enemies of scale, of true scale. So I had the opportunity to work on the Sochi Game Times website, which has an incredibly asymmetric workload. There were about 100 content editors and many, 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 many million viewers. Most out-of-the-box CMSs have one data store that says you write from this and you read from it. I have 100,000 times the load for read as for write, and I want to use the same physical store. That becomes an instant choke point. So what we see in a lot of the really high-scale architectures is an explicit bifurcation of mutable and immutable operations. Anyone using Hekaton? Sorry, I'm not even allowed to say that. The SQL Server in-memory stuff? A couple hands. It uses the same technique. In the, one of the new capabilities in the latest version of SQL Server is you can basically have fully in-memory managed tables. And when you read from them and write to them, essentially two different I/O paths. It's one of the reasons they can get pretty incredible scale. Same philosophy and same approach applies. In the particular case of the Olympics, we had a system for editing, which then pushed a feed to publication, which is explicitly designed to serve relatively slow-changing content very quickly to an enormous number of people. But two different systems with two different sets of physics. And the last piece is I have no way to add more capacity at each tier. Adding capacity to the front end, easy. Add more VMs, it's just a PowerShell call. Adding capacity at the back end, I could add more SQL servers, but nobody knows how to use them. The code's not going to instantly adapt. The BI system's not going to know how to work across them. So that's a little challenging. OK, so let's take this and let's just apply the most basic kind of cloud-native architecture. We're going to put some queues in the middle. Instead of writing directly in and having that, that chain tied, let's instead say, OK, the most important thing is to be able to receive that work, park it safely, and then get back to it, so that I'll never be inserting or I'll never basically be doing work at the rate at which data is coming in. Our good friends queuing. So let's just make a few small architectural changes. So I'm going to use an Azure queue, the simplest possible thing that can fulfill this scenario, because I don't need PubSub. I just need cooperating producer, competing consumer to fan this work out. I don't have any ordering guarantees. I don't basically need to process messages one after the other. And once I drop queues in there, I'm going to get rate leveling for free. Any ingest spikes will just basically write into the queue and we'll absorb it. And when we look at the scalability points, it'll make sense as to why I'm not worried about that. And then it actually unlocks the ability to go chunky on the other end. Rather than taking one upload and putting it into a database at a time, I can grab 4, 5, 6, 7, and then do a batch insert. And chunky operations are generally going to beat chatty ones any day of the week. So the only thing that's different now is instead of when I get the 200 OK back to the store, it's not saying I have processed your data and it's now available for reporting. Now the implicit contract is I have your stuff. I'm going to get to it fairly soon, but I'm not going to tell you when, but you don't need to care. I have securely received your data, parked it somewhere durable, it's OK. We're trading latency for throughput. We're making an explicit choice that I'll take a few seconds, a few tens of seconds, whatever it happens to be, of latency on the back end in order to not go down in production, or not to go down because of back pressure. Seems like a good trade-off. So let's just walk through and see how this has changed our system. So scalability, Azure queues. I get about 5,000 ops a second, which in practice for an insert, get, and delete works out to about 2,000. If I've got 1,000 or 2,000 stores posting every minute, I feel pretty good about a single queue. And if I needed 10 queues, and I've run some systems with several hundred queues, then it's basically just round robin, or just basically bucket hash across them. Pretty simple technique because they're transient. And these scale out quite well. And this will give me my back pressure relief during load spikes. So this improves my write capacity by decoupling. What I haven't talked about is read, basically improving my read capacity. I won't go into it too much in this one. But the simplest way is to basically, instead of pulling directly out of that central consistent store, I'll just pull data out, put it in a distributed cache, and noodle on it from there. So again, very common pattern where I can add both read and write, mutable and immutable capacity. Okay, so now we just come and break down. We kind of look at some SLAs and some availability. So it actually kind of looks like, oh, I thought I had a calculation there. Now that I have 4 of these to put together, I actually lost about 1/10 of a point on SLA. It's actually 99.74% now. So you may go, hey, I just gave up. I actually now have a worse SLA. Not really. Now what I've actually done is I've traded my, for the workflow of receiving data, I've actually traded the 99.9 from SQL DB, which basically says I can connect, but I may not be able to do an insert, to the, yep, you'll be able to do an insert as long as you don't go past 2,000 messages a second. And if you do, we'll give you a bit of back pressure and you can come back. So that seems reasonable. So we, now to insert, we have no direct dependency through to the backing store. And if we needed to do some transient error handling, again, to basically handle any little hiccups against SQL, it might blow up the back-end process, but it doesn't affect receiving messages. We're now decoupled. Again, trading latency for availability. We always have these knobs around consistency and latency for availability and throughput, and we'll end up basically playing with them a fair bit. Oh, it's this way. OK. But that was just SLAs. That actually doesn't say anything about the experience that we're going to deliver. That doesn't say anything about the business value that will be generated. So let's dig in a little bit deeper here now and kind of muse over, what does this really mean? SLA calculations, they're only going to cover my dependency availability. They're not going to do a thing about bad code and weird load. And I will stand here and say and freely admit, I've written some awfully dodgy stuff in the last couple of years. And we'll all have those moments too. But ultimately, we need to be delivering value to the consumers of our service, workload by workload. Some workloads are worth more than others. There are things we will do in the systems that will be essentially be worth more money. They'll be worth more value. They'll deliver more useful things. So the next step I tend to go into when doing these is to actually trace all of the message paths through the system, is to look at the end-to-end code flow and look for those little interesting aspects. And we've gotten pretty consistent. I don't deviate from this no matter what the type of system. Start from the first point a message comes in, walk all the way down, walk all the way back, and just at each point, especially when you cross a process boundary going, are there choke points? Are there contended resources? Are there bottlenecks? And what are the error modes, at least the common ones, that can happen? And how does my system respond to that? OK, so this is ultimately, this is the code path that I would generally tend to implement. I'm going to do a DNS lookup. I'm going to open an HTTP socket. I'm going to hit the software load balancer. I'm going to have some form of HTTP listener, either a high-level one like Web API hosted in IIS, or I might go bare metal down on top of HTTP sys with something like OWIN if I'm doing a really high-end kind of dense application. I'm going to take that incoming web request. I'm going to run it through some business logic, figure out what it is. I'm going to authenticate. I'm going to validate. I'm going to transform into something else. In this case, I'm just going to go and publish to a queue, whereas before I would just call SQL. And that'll take a dependency on Azure Storage, which will in turn take a dependency on my ability to authenticate against that API. So the first question I ask is, well, does this solution require node affinity, instance affinity on incoming connections? Well, in this case, the front end is completely stateless. You can hit any one of those nodes and be fine. If you did need to pin to a specific node, for whatever reason, a lot of gaming applications actually require direct affinity because it takes too long to round trip state through storage. It's kind of a problem, especially if that instance goes away. Luckily, this particular app, not a worried. So I can go, OK, no availability points there, no real scale issues to worry about. We'll just keep on going. This is where things start to get interesting. This is where I keep coming back to asynchronicity. And especially in the Windows and .NET stack, this is pretty critical. But Linux works a little differently. So this challenge gets handled in a slightly different fashion. So ultimately, it comes down to how many concurrent requests can we put through the HTTP sys pipeline. By default, it works out to about 12 times core count parallel dispatch threads, because it's a bounded concurrency dispatch system with a front-end queue. So I get a certain number of, essentially, we'll call them workers, for lack of a better term. And while someone else is in that line, no one else can be there. If I'm synchronous, even if I'm waiting for someone else to complete, I'm blocking that lane. If I'm blocking the lane, or they all get blocked, just like being at the grocery store, and that application queue gets up to about 5,000 by default, that web server goes into 503, service unavailable, horrendous error message, come back later maybe. Not so good. And long-running activities can and ultimately will block the queue, any high latency code paths. And these are the sneaky ones. These are the ones that will come up. So ultimately, our only real choice for a high-scale, high-end service like this is to make everything asynchronous and bound every single downstream call. 2 stories on this one. I was working on a site. I'll show the slide, graph from that in the next slide. About 3 years ago, where they had one particular call out to an external service that got called very rarely. It blew up. Show the result in the next one. I'll call us out. Visual Studio Online, back in November, had a couple-hour outage. It was one of the calls to an external authentication service went down. Those calls were not bounded. They weren't bounded they were bounded in time. They weren't bounded in concurrency. So each individual VM in that service was creating hundreds of outbound connections to the other service endpoint. I talked about those less than obvious metered resources. I have one VIP that hosts my service. I have another IP endpoint that hosts that service I'm depending on. And the size of an IPv4 routing table is 64,000 items. And if I'm creating hundreds of outbound connections per instance, I hit that limit very, very quickly. I can't establish any more outbound connections. I can't authenticate. All the pipelines freeze up. And I go down until that backlog clears itself out. So this is one of these interesting things that happens under high load conditions with a partial failure of a dependency. So to put some numbers behind it, I had to remember the computers over there. So this is a graph from a production site running 240 cores just for front-end web servers. At the time, it was fully synchronous, and this was before .NET 4.5, so there was perfectly valid reasons. Doing begin open APM-style chains is ugly and hard and painful and nasty and happily completely unnecessary these days. And a single call, 0.5% of all traffic, blocked. That external service had a hiccup. It was about a 6-minute outage. The slow requests dominated the entire system within 3 minutes and brought the site down. So if you've got a monitoring system that gives you a performance counter every 5 minutes, I can guarantee that Twitter will know you are down before your monitoring site does. But that's a different presentation. Again, just showing that tie. Because I don't know about you guys, but I've never waited 400 seconds for a website to render in my life. And I first cranked open Mosaic in 1994, and most things took a long time to render back then. So asynchronicity, those hidden shared metered resources, they will pop out in the most unexpected ways. All right, so let's go to authentication. Authentication is tricky. This is one of those really hard choices where authentication's hard, security's hard. You want folks who specialize in this to take care of a lot of the things because there's so many things you can get wrong. This normally shows up as, I don't want to manage secrets myself. I don't want to manage user IDs. I don't want to manage passwords. I don't want to manage, I don't know, credit card information from a POS device. Sorry, that one was too easy. This stuff's tricky, and it is really easy to get wrong. So often what we'll want to do is we'll want to federate. We'll want to take a dependency on a highly trusted security service to basically say, this incoming entity is who they say they are. Here's the roles that you have assigned them, and you can decide whether to enable or disable certain actions. The challenge is, and though actually the trade-off, and there's always trade-offs, is now you have an absolute hard dependency on that external service. Because if you cannot authenticate, generally, for well-behaved services, you cannot get in and do things. So if your authentication system is down, you are down. And that may be going, okay, that's the right trade-off. The engineering risk of building our own secret management system is so high, we just don't want to go there. That's a perfectly valid and actually generally recommended approach. The only delta is you probably want to leave yourself an administrative account on a very well-protected pre-shared key. Because if you can't get in to look at what the site is doing, because you have the only way in is through that single point failure service, you're going to have some interesting things to explain the next day. So in general, I I generally push people towards take a bet on a federated security service like Windows Azure Active Directory. You probably don't want to build your own secrets management system. And if you do, you want to put a lot of work into it and make sure you have folks with a lot of expertise have a look at it. But for your operational roles, make sure you have a second authentication channel. And actually, even more importantly, for services that you consume, things like, folks using Service Bus in the room? Okay, do not ever, 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 ever use ACS authentication against Service Bus. Because you've taken a service that has a reasonably high SLA and bounded your usage of it with a service that has no SLA. Because ACS is essentially still in preview. It doesn't have an SLA associated with it. If you're going to use something like, I'll just use Service Bus as an example. If you're going to take a dependency on that service, always use the shared access signature token support that it has, which gives you a time-bounded pre-shared key. That way, your vulnerability is very strictly bounded to when you have to essentially reissue that token, which will happen far less often than you'll actually need to establish a new connection and do useful work. Probably one of the top 3 failure modes that I've seen in kind of live cloud services has been an authorization or a security failure, which the system was running fine, but no one could get in and do useful work with it, which is always a very fun day. Right. So let's look at the queue. I'm assuming that we can write validation functions and not blow up. I'm going to assume that we can do data transformation and not blow up. That's what try-catch statements are for. But let's think about this queue. The first one is fairly minimal chance of happening, especially in this particular scenario. I'm not likely to exceed 2,000 messages a second when I only have 1,000 stores. But there is absolutely a case where it'll happen, which is I trip a bug in that unknown application that's sending me data. It decides to go crazy someday and just send me an update every second or 100 updates every second. I've seen it happen, where some unknown, authorized, authenticated, validated entity coming into your system just has a very funky day and decides to go crazy. So what do? In this case, I'd probably start load shedding like crazy. Going, hey, this is a very unexpected event. It wasn't worth putting the engineering investment into, or maybe it wasn't, or maybe it was. That's why we talk about these things, and you tease through and go, oh, what's the likelihood? What's the ROI? What's the investment required? In this case, I probably wouldn't bother with queue scale out, other than that when I implemented the code, I wouldn't write directly to the storage APIs. I'd have some interface in the middle so that I could swap out a multi-queue provider or a different messaging service if I needed better, different capabilities in future. But the message size, that's a fairly interesting one. And this actually could be quite likely. Say, for example, again, if I trip some weird element, a new version of an app or firmware goes online at the store, and they decide to send me a really big, fat, happy message. For example, most of these systems are going to be built as store and forward. If they lose network connectivity, I'm going to buffer up data locally. And when network connectivity gets established, I'm taking that big thing and just shoveling it right out. And maybe people misunderstood the spec, and rather than sending 10 5-kilobyte messages, they sent one 200-kilobyte message. Maximum message size for a queue, 64K. Someone shovels this huge thing up, I've got a couple options. I can barf an exception and hope that there's appropriately store and forward logic on the client to handle that, but it'll probably just keep retrying that poison message. I can scream for help and drop it on the floor, but then I probably lost data. Or I can say, this one's actually fairly likely and is a small engineering investment for me to take care of. So I'm going to take the incoming message, write it out to blob storage, and then put a pointer in the queue. When you come to the talk tomorrow, I'll show you the code for doing that. But this is just one of these subtle little things that this message size is a metered resource on the thing that I'm targeting, and I have a medium likelihood that someone could misbehave and send me something really big. So it's probably worth going and investing and making that change and mitigating and mediating around that. Okay. You guys have been absurdly quiet. I mean, the microphones aren't electrified or anything. If you guys don't start asking questions, I'm going to start picking on people I don't know. People I do know are fairly safe. They know I pick on them on a regular basis. I know it's the end of the day, but I mean, the coffee's served. Come on. Okay, so let me just kind of flick over, and we've covered kind of the scalability points. We've covered the availability points. Just got through that fairly quicker than I thought I would. So let's, I can do a couple things. I can flick over some code and actually illustrate what some of these things look like in that context. or we can kind of talk a little bit more about some of the interesting anti-patterns that happen, or we can kind of go all upscale. This is the choose your own adventure section because y'all were too quiet and I expect you to ask more questions. They're like, who is the crazy person up on the stage and why is he making me do things? Anti-patterns. Ah, fun anti-patterns. So I can give you anti-patterns in like those Visio-looking diagrams, or we can just get nerdy and show some code. If you had said anything else, I would leave. Just give me 1 second to fire up the other device. No, really, fire up the, oh. Apparently 5 and 6 are different numbers. Okay, so nothing I am about to show in my less than optimal code path, none of this is made up. I have seen examples of this in production, in any number of production sites. So let's just start with just a bog standard web API controller. And I got nice comments, and it's all very pretty, and it looks great. So let's just go through and tease out some of the more common things that I see. And you might laugh and go, no, really, this stuff happens? It does. So right off the bat, I've said that I know I'm an IO-bound workload. I know that my only job in life is to take stuff in, massage it slightly, and shovel it out to something else in a different format. So as soon as I'm running synchronous, I am throwing money away. And you know, from the Microsoft perspective, that's kind of cool. You want 10 times as many VMs to run your site? We'll sell them to you, or rent them, really. But for the purposes of your own bottom line, you may not want to do this. And the worst part is, if it was just a money thing, if it was just I needed more capacity to run my site, I'd probably be merely leaving this one out. But it's an availability issue as well, because anything blocking here, and I have some blocking stuff later that I deliberately put in, and you'll laugh when you see it. This can bring my site down. This can provide an unavailability event. So why bother logging invalid data? It's not like it would be useful for debugging or catching bad client builds or anything. Top 5, all-time, fun little things. Very few systems that I've worked with, unfortunately, capture invalid data and log it in a raw form to go back and look at later. The most common form of this is there is no such thing as a globally atomic client application update. In many cases, especially with mobile devices that require user interaction, you have 2 choices. You either get the user to click, yes, I want the happy new thing, with 3 choices. You get them to click the happy upgrade path and justify your investment in a new app. You let them continue using the old build and whatever it decided to shovel to you, or you play Xbox and say, go away until you click yes. If you choose the middle option, there will be a broad range of things shoveled to you at any given point in time. And the most common thing is you've got a build of your service out there that understands a certain set of messages sent to it. But it doesn't understand either an older one or a newer one, depending on the timing. Because there's always going to be multiple versions of stuff in place. If you don't have a way to say, I don't know what this is, but that doesn't mean it's bad. It just means I don't know what this is, and a way to log it and go back and look at it later and either go, oh, for some whatever reason, like 5% of our clients are still running this beta build. How did they even get their hands on that? It's going to be extremely difficult to diagnose this class of things. So, separation of concerns. So I was working on a project about a month ago. IoT-style app, connected devices. It was pretty cool. The entire application was in one file, 2 classes, 16 functions, from everything from the web API. Actually, sorry, it wasn't. It was actually WCF, but let's not talk about Complication Foundation, shall we? The last time I threw that joke out, nobody caught it. Or they just thought I was, you know, they're like, he said what? And he still has a job? Anyway, all the way from the kind of the web service front end to authentication, authorization, validation, down to the database in 2 files. I was looking at this and going, maintainable, yes. This is why we're here. So I talked earlier a lot about that throttling behavior. They need to basically exhibit back pressure. I have seen 3 systems in the last year that implemented back pressure management by sleeping in the frontier and occasionally pinging. I went, noble intentions. Excellent. We have a place to put the right stuff. Unfortunately, the sum result was basically to block the lane, tie up 10% of the actual useful capacity in that machine, and not actually be friendlier to the back-end systems, because the only thing is rather than actually rate leveling, this would be the equivalent of we'd all stand up, look at the door, and going, I'm going to wait a few seconds, and then I'm going to rush the door. And with enough folks in the room, enough of us would choose to rush the door at the same time that it only exacerbates the problem. It looks great if you only have one machine. If you have dozens of machines that are not coordinating this, even with jitter, we all rush the door at the same time. And the folks outside are going, you have some crazy people in here. All right, so configuration, who needs it? Let's just hard code stuff because it's faster. Honestly, I really wish I could make this stuff up, and I know we absolutely have to do better when it comes to configuration management and secret management in our tooling, but I still see a lot of this stuff. I still see secrets, magic numbers, things hard-coded in. I actually don't have any idea how this stuff gets tested because, well, oh look, we use our database as our test platform and our dev platform. All right, this is probably one of the single biggest changes for folks to adjust to, moving from SQL as Titanium to SQL as external service endpoint that lives magically somewhere else. How many folks have seen code where con.open was just there, where a SQL connection, that beautiful conduit to all things relational, was assumed to be like oxygen? It just happened. And if it didn't happen, you called up IT and you yelled at them to get a better network. Entire generation of developers. And this is actually really cool, by the way. We had a server platform that was so good, nothing would ever go wrong here that couldn't be fixed by shoveling another $1 million worth of hardware at it. It's actually really great from a software perspective. But when we move from that titanium eggshell to it's just another external service, this is problematic because that resource may be hiccuping. The network may be in the process of rerouting and retransitioning. All sorts of interesting stuff can happen. So everything will be fine until it's not. I could not bring myself. I could not do it. I could not write SQL injection code. I tried, and my fingers locked up. I tried to string format the data in there, and it just wouldn't work. I apologize for that. I find it amazing, disgraceful, painful, and occasionally hilarious that it's 2014 and I still see SQL injection attacks in professional code. I know no one in this room would do it, and if you do, well, don't admit it because that would be bad. It's scary, but when you're going through code bases, especially for folks in consultants in the room, especially when you're going to a new client and you're kind of taking on some partial guilt for their code base, these sort of things are way more prevalent than I'd like to admit. It horrifies me. One particular code base I was looking at about a year ago, probably, I don't know, about a 100,000 line code base. 32 seconds after I'd opened up Visual Studio, I called the project manager and said, we need to kill this with fire. Because I did just what we're doing here now. I started at the message endpoint, I went F12, 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 SQL injection. And that was enough. As soon as I saw that red flag, it was like, there are deeper problems here if I found something that bad that quickly. All right. So we'll actually catch exceptions, because, they happen. But logs are for wimps. But today, when I wrote this code, I didn't write it today. I wrote it yesterday. I'm a wimp sometimes, so we're going to log this exception to the one thing that we know. We're going to log it to our friend. We're going to log it to SQL. Now, if it was a SQL exception, this might be a problem, but that never happens. So two interesting anti-patterns here, just to kind of pull it back. If you have telemetry data going into the same data store as operational data, they will contend. And if there's no prioritization, if there's no QoS between them, telemetry usually wins, which is usually not the best result. This has brought down, this is a long time ago now, we've gotten better at this, this has brought down internal Microsoft production services by putting operational and telemetry into the same storage account. They must be isolated. And they really should have different underlying dependencies. Because at the end of the day, this is the only way you're going to know if, hey, if something's gone terribly squirrely. And I still couldn't bring myself to write an injection attack. So, but here's my favorite. This one was responsible for me being up at 4 o'clock in the morning looking at ETW traces. So I don't know why or how this became, unfortunately, mildly prevalent. Everyone familiar with the difference between throw and throw exception? Cool. The call stack. The call stack. I've seen a lot of code like this, and I'm pretty sure there's resharper or ethics cop rules you can use to find it. But essentially, especially in a world of a lot of task-based or a lot of async code and a lot of threading code, where you may not have basically the functional name context if you use a lot of Lambda functions, what this will do is we'll throw away the entire trail of breadcrumbs that says where this problem came from. And all you'll get is the enclosing function. This is pure evil in 8 characters. And the only reason it's 8 is because I had to put a space in there. Was working on a project about 2 years ago. Got a bug, basically a bug report. Whole thing blew up. Everything died. Azure's terrible. We're like, okay, we think differently, but let's come have a look anyway. What was happening was, as part of the retry handler, they'd actually bound in saying, hey, if an exception is thrown, please do this. And that exception was being marshaled on essentially free thread, on a background thread. And we all know great things happen when you throw uncaught exceptions on background threads, right? You get an opportunity to reset the machine. That's a good thing, right? So as part of the error handler, it was grabbing the exception, logging it, and then rethrowing it like this. So of course, on the very first normal exception, like, hey, I got a bad message, I just needed to do something with it, the entire process was being brought down. And because logging is generally asynchronous, and you don't want to immediately post to an external machine, that would be auditing, all we had was this little bit of exception text that says, hey, error was thrown in retry handler. OK, that was weird. This one, unfortunately, shows up a lot. And of course, then there's the same thing on the other side. You know, the standard gets, direct dependency, all that good stuff. And well, I had to throw that one in for fun. Because even if I authenticate, no one's ever going to send anything bad. No one's going to fat finger a client update, right? Or the mobile app developers, client side, anybody? Well, maybe they're too scared to show up here. Clients do weird things, especially if you don't control them. If you only own one end of the pipe, very strange things will happen. There goes a client developer. I had to heckle one person. So it's so critically important to be able to, you're going to be able to accept a lot of stuff. Even coming in on validated, authenticated, authorized connections, you can still get strange stuff. So you've got to handle it. So with what short time we have remaining, I'm just going to flick back and kind of just talk about a couple of the, if I can find my clicker thingy. OK, so tomorrow we'll go through how to build it right, or more right. It's called the more optimal solution. And I'll throw in a few more of the patterns and kind of go into a little bit more detail on the code. But just kind of takeaways. We're always balancing kind of those 4 pillars: scalability, availability, manageability. And the most important one is, can we actually deliver this thing relatively on time and relatively complete? These are all trade-offs. There's no one magical choice. It's always a balance inside what are our business priorities, what do we have time to do, what's most important. I actually want to go home at some point, and I write really bad code when I haven't slept in 2 or 3 days. How do we add more capacity at each layer, and how do we use it more efficiently? This is where telemetry will come in terms of knowing where you're actually using, where you're not using capacity efficiently. Actually, I was debugging one today. So I actually got a call, system saying, hey, we're doing this thing. We just brought it up into Azure, and Azure's horrible, so our app runs slow. We're like, really? I don't believe you, but I'll have a look anyway. And it turned out that it was taking about 9.5 seconds to render a web page. We're like, that seems unusual. And since this is an internal application that I might actually have to use soon, I have a vested interest in making it suck less. So we took basically a profile trace, and we're going, OK, so to come in, kind of page render, 10, 15 milliseconds, pretty cool. Call out to cache to pull down a data block, call up 100 milliseconds. That data object might be a little big. That's a little concerning. 8.2 seconds to deserialize the object. I think we have a problem here. It shows up in the most interesting of ways. There was lots of capacity in the system, but it was being used very inefficiently. And when this system had been deployed on premise with capitalized hardware for 2 years from now, it just got lost in the background noise. Nobody noticed. You put it on smaller machines, but more of them, the seams start to show up. So having rich telemetry, having App Insights or New Relic or App Dynamics or your profiler of choice, I like Ants, and having that rich data so you're not doing psychic debugging is incredibly valuable. Psychic debugging is fun, but not that efficient. And for these types of open-ended systems, how do you buffer and absorb shocks to the system? Whether it's everyone decided to rush at once, you got amazingly wildly successful, we love that, we all want it, we all want to be ready for it. And how do I handle when some of the things that I've taken dependencies on, because I can't build everything from scratch because I need to move fast, has some form of hiccup, interrupt, something. All right, so that takes us to the end of our time. Feedback, you can just come tell me, but they tell me these official things are important, so hey, please. The next session happening at 5:30 in Hall 1A is going to talk about how we basically built all the back-end services for Halo. Highly recommend checking that out. There they go into how do you design for a few 100 million people in a highly stateful service in memory. Extremely cool stuff. I'm going to hang around for a few minutes off to the side if you want to ask questions or come grab me some point during the day. And thanks for sitting through an hour of bit of fun about services.